the same. All right. We need to derive the equation of motion. It means that we need to derive the dynamics of the system. How can we do this? Pretty much the same as we already did it for the mass spring damper system. So we need to derive a Lagrangian equation for this system. First of all, we need to derive the Lagrangian. A Lagrangian is the difference between kinetic energy and potential energy. For a mass spring damper, we only computed kinetic energy of one body. Right here, it will be kinetic. It will be sum of kinetic energy of the bodies. The same for the potential energy. We need just to sum potential energy of all the bodies. It will be the energy of the system. So right here you can see the kinetic energy of a system that consists of two terms. By the way, here it simplified version, such as all mass considered as a point mass. So it's not a rigid body with inertia, but all of the mass is located in the center of mass, like in a circle. And this is why we do not have any terms with angular velocity, just to make it simpler. So kinetic energy 1/2 times m times v in power 2, where v is the velocity of center of mass, right, for the first link and for the second link. H is just the height, the y component for the center of mass, right? Okay. How can we compute H? We just need to solve direct kinematic task, like this, but not for the end effector, for the center of masses. How can we compute V? We need just to take a time derivative of it. So H and V we can find if we will compute direct kinematic task. So it will be V's, V1 and V2 in power 2. Do you agree? And if we'll put everything inside, we'll have those terms for the kinetic energy and those terms for the potential energy. Do you agree? Okay. We have done halfway. If you do remember the earlier Lagrange equation, in order to derive it, we need to take a partial derivative now. So we take this, that Lagrangian, and we need to take a partial derivative to the q and to q dot, right?
Can we, on the previous slide, shouldn't the first term of the potential energy be L1 over 2?
Over 2. Here, look. It's over 2, but also we need to. It's like alpha 1 divided by 2 in power 2. We have 4 here plus times 2. In this way, we have 8. Mm-hmm. Okay. So we need to take a partial derivative to the q for the first generalized coordinate for the q dot. Then we need to do the same for the q2. So we will have those terms. It's like you can do this by your hand on a piece of paper. And then if we'll put everything inside, we'll have equation for the torque, tau 1, and for the tau 2. Okay? Now you can see that that we have terms with q double dot. So this is q double dot, and you have a huge term next to q dot. So this one also. It for the first link. Also, you can see it for the second link. Okay. What else can we see here? We can see that we have terms with the velocities q dot, not acceleration q double dot, but just q dot, right here and right here, right? And also we have terms without any derivatives, like this. And actually we can rewrite it in a matrix form, and it will look like this. So M will be matrix of inertia. It's just like in second Newton's law, that torque equal to the mass times acceleration or force, it doesn't matter. It's like F ma. But here we consider not a point mass, but a mechanism. And mechanism has where is center of gravity of a mechanism? It's not a constant. It is a function. For example, right here my center of mass right here, but now it's right here, and it is not constant. It's changing, and due to this fact, we describe mass not with the constant like m1 plus m2, but with the matrix that depends on q, on the position. Then we have components that I mark with the blue. Those are called Coriolis and centrifugal forces due to the way how our planet moves. And Q, it is the just gravity. So those orange are just gravity. And if you take a look at this, you'll see that it's pretty much gravity forces. Okay. So this is the equation for a robot manipulator. It is true, this equation is true only for a robot which is fixed to the ground. For a walking robot, it will be a little bit different, but we do not tackle it in our course. Okay, so for our system, we can nicely compose everything into these matrices. So now it is not so scary at all. All right, but what can we do with it? For example, we can do the same thing as we already done it with the mass spring damper system, and we can use basic simulating blocks, and we can create a simulation model if we want to. But for now, we consider modeling not for simulation, but to control.